To us mere humans, Earth is vast. It takes days to travel from one side to the other. But leave the surface and it quickly becomes clear that we live on a tiny speck in a colossal universe filled with innumerable planets and countless stars residing within trillions of galaxies. The universe operates on a scale that we simply cannot comprehend, let alone exhaustively explore. But within this grand structure lie individual beasts that, on their own, defy our understanding of scale. Stars so large, they make our sun pale into insignificance. And in the depths of the southern constellation Scutum, we think that we found the largest one yet. But just how big can a star get? And are there even bigger beasts waiting to be found? I'm Alex McColgan and you're watching Astrum. Join me as we climb the cosmic beanstalk into the kingdom of the universe's giants. You might think our sun is pretty big, and it is. With a radius of 700,000 kilometers across, if the sun were a football, or a soccer ball for you Americans out there, the Earth would be 109 times smaller, the size of a 2mm wide peppercorn. Even if you added up all the mass of all the solar system's planets, the sun would still be 743 times more massive than all of them combined. But when it comes to other stars, our sun is nothing special. Some of our closest neighbors, the Alpha Centauri binary stars, are a similar size, and Sirius A is twice as big. But how big can a star actually grow? To understand that, we need to look at stellar evolution. So our journey begins here, in the heart of something known as the Hertzsprung-Russell diagram. Independently invented in the early 1910s by both Danish astronomer Einar Hertzsprung and American Henry Norris Russell, it plots stars' temperatures against how bright or luminous they are. And running down the center of this diagram lie what's called main sequence stars. This spine is where most stars spend the majority of their lives. If they're here, it means they're in a stable phase of existence. Having gone through the chaotic molecular cloud collapse of birth, a main sequence star is now continuously fusing hydrogen in its core, generating energy that pushes outward against the brutal inward force of its own gravity. It's a balancing act, and once it's reached, a star is said to be in hydrostatic equilibrium. Almost all of the stars on the main sequence are in this state of so-called rest, but that doesn't mean they are all the same. Our sun sits comfortably in the middle of the Hertzsprung-Russell diagram. It's a fairly average G-type main sequence star. The G is what's called the spectral class, which essentially classifies stars by their temperature and therefore color into a seemingly arbitrary naming system of O, B, A, F, G, K, M, where O is the hottest and M is the coldest. I remember it using the mnemonic, "Oh, be a fine girl, kiss me." Do with that what you will. The Sun and other G-type stars have surface temperatures around 5,778 Kelvin, giving them the yellow-white hue that we're all familiar with. Their cores steadily fuse hydrogen into helium, converting about 600 million tons of hydrogen per second and emitting energy that, in the case of our Sun, has powered life on Earth for billions of years. But if you move up or down the main sequence, the stars change and a pattern begins to emerge. It's probably not surprising that dim stars are usually cool, and that the hotter a star gets, the brighter it gets too, at least on the main sequence. But what might be less intuitive is how a star's mass relates to this. And there is a clear correlation. The brightest star also tends to be the most massive ones. Take, for example, Bellatrix, the 26th brightest star in the sky and the left shoulder of the Orion constellation. It's a B-type star, one of the brightest classifications, and has a surface temperature around 22,000 Kelvin, almost 4 times hotter than our Sun. It's also 8.6 times more massive. The effect of this greater mass is to crush the hydrogen in Bellatrix's core far more than in other stars. Greater pressure increases the rate of fusion reactions, and therefore, far more energy is released. This fusion is so powerful that it forces the star to swell. It's as if gravity almost can't contain it. So Bellatrix's volume is a whopping 200 times greater than our Sun's. But this comes at a price. Massive main sequence stars burn hot and fast. While the Sun will likely have a total lifespan of 10 billion years, Bellatrix has been burning for 25 million, and there's only 7 million years left. This actually makes large stars quite rare. Their instability and rapid existences mean we're simply less likely to see them than their longer-lived, less massive cousins. So, is that the answer then? If we want to find the largest star, should we simply seek out the heaviest? It's thought that stars can't grow much bigger than 150 times the mass of the Sun without becoming so unstable that they blow themselves apart. However, the universe has found ways to cheat when it comes to this limitation. When two massive stars collide and merge, the resulting star is a true behemoth, much larger than anything possible through the slow devouring of an accretion disk. Perhaps this is the explanation for the truly staggering and excitingly named R136A1, potentially the most massive and most luminous star in the universe. At the furthest top left point on our Hertzsprung-Russell diagram, R136A1 is a monster. Forget the 150 times mass limit. This beast has been estimated to be 265 times the mass of our Sun, and has a radius 40 times larger. It's part of a particularly rare group known as Wolf-Rayet stars. We found just 220 in our galaxy, although scientists expect there could be as many as 2,000. They are massive, and in an advanced but short phase of life, one that comes just before they collapse into supernova explosions. Because they are so unstable, they throw off vast amounts of plasma in great winds, ejecting as much as 10 solar masses every million years at speeds of up to 3,000 kilometers per second. But they are also incredibly luminous, with R136A1 releasing as much light in just 4 seconds as the Sun produces in a year. Although, to our eyes, it's actually only 164,000 times brighter than our star, because most of its radiation is UV light. To be honest, we're lucky to have seen this star at all. It will likely only exist for 3 million years, the blink of a cosmic eye. But this still isn't the universe's largest star, not by radius at least, because although it is certainly one of the most massive, there are far less massive stars that grow much larger. How? It turns out, the very largest stars have a trick up their sleeves, or rather, in their shells. So far we have focused on main sequence stars, those burning hydrogen in their core. However, as a star dies, eventually that hydrogen will run out, and without the explosive energy of fusion to keep it stable, a star's intense gravity causes its core to start collapsing. With this comes even greater pressure, which once again turns up the heat in the core. Eventually the core becomes hot enough to kickstart helium fusion, causing the star to enter an entirely new phase of life. But this heat is also enough to warm the outer shells of a star. They can reach temperatures that used to only exist at the center, and suddenly, hydrogen atoms in the outer layers are also able to start fusing. This causes the star to expand dramatically as it becomes a red giant. Our Sun's radius is currently 700,000 kilometers. But when this process begins, the Sun will expand to a diameter of 300 million kilometers, which will make it big enough to consume Mercury, Venus, and possibly even the Earth. This process can take place in stars 0.8 to 8 times the mass of the Sun. A current example of a red giant is the fascinating Mira A, which is part of the Cetus constellation. It's only between 1 and 1.2 times as massive as our star, and yet its radius is at least 332 times bigger. And this is just the baseline. Mira A pulses over the course of various 80 to 1000 day cycles. When those cycles align, Mira physically puffs up, so its maximum radius is actually much larger. It can reach around 402 times that of our Sun. But even a red giant isn't the biggest type of star. When you get to 8 solar masses, another classification appears, one that's even bigger. The red supergiant. Towering, mighty, vastly larger than their smaller cousins, but also doomed to a tragic end. These monsters of the universe will end their lives in an explosive supernova. But we're interested in the moments before that, when they swell to become the largest stars we see in the universe. Betelgeuse is one of them, with a diameter of 1.2 billion kilometers, making it more than 700 times the size of the Sun. If it was at the center of our solar system, all the rocky inner planets would be engulfed. Even Jupiter wouldn't escape. Now, these supergiants are violent beasts. In the last throes of their life, they pulse and throw out huge amounts of material, which makes it difficult to determine where the edge of the star ends and space begins. But despite its enormous size, we know even Betelgeuse isn't the largest star out there. There is one other candidate, and as I hinted at the beginning of this video, it lurks in the constellation Scutum. This is UY Scuti, and it is colossal. So vast that 5 billion suns could fit within it. Surprisingly, it's not very hot. In fact, it's 40% cooler than the Sun and glows a somber red. Another red supergiant. Because of its vast distance and low temperature, UY Scuti is not actually visible to the naked eye. You need powerful binoculars or a small telescope to spot it. At a distance of 5 to 10,000 light years, there is some uncertainty about UY Scuti's true size, with many other candidates vying for the title of largest known star. But UY Scuti won't be around for much longer. It's already 10 to 20 million years old and may now only have a few million years left on the clock. Within that time, it may even get smaller, transforming into a yellow hypergiant. This class of star is incredibly bright, but in order to achieve this, it would first have to shed its outer layers, becoming even hotter to sustain the last possible fusion reactions. Hypergiants are capable of blowing off the mass of Jupiter in just one explosive burp, and they have lots of them. Filled with heavy elements like oxygen, carbon and nitrogen, these ejected materials can form vast clouds 10,000 astronomical units in length. That's 300 times the distance from the Sun to Neptune. And they are vital to the universe's development. These swirling expulsions mix with dust clouds and material from other stars, combining to create stellar nurseries filled with the ingredients for life. This is still several 100,000, if not a few million years away for UY Scuti. But there is a giant star that's even closer to this final destruction. We've only ever properly imaged one star outside the Milky Way, and it was WOH G64, a red supergiant, a bit like UY Scuti, 160,000 light years away in the Large Magellanic Cloud. Recent studies suggest it may have already turned into a yellow hypergiant. In the last 10 years, it has become dimmer as it's thrown off material and become shrouded in dust. The problem is, once you get to these distances, it's hard to measure things precisely. Maybe WOH G64 is actually bigger than UY Scuti. We don't know if stars can get bigger than this. It's unlikely, as giants like UY Scuti are scraping the edge of what's called the Hayashi limit. This is the maximum size a star can reach given its mass, and you can see it as a line on the Hertzsprung-Russell diagram. If a star crosses this line, then convection inside takes over and gravity starts to win, making it smaller. So one day we might find a star slightly bigger than UY Scuti, but it won't be by much, unless we're missing something. Perhaps there's a type of giant star we simply don't have in our galaxy. We don't know, and unfortunately we don't have the technology to find out, yet. What I do know is that humans can't really wrap our heads around anything bigger than a few thousand kilometers, so the scale of the biggest stars is far beyond our comprehension. They are cosmic monsters. But in the grand scheme of things, even these stars are tiny. Galaxies are tens of thousands of light years across, millions of light years apart, and individual filaments of cosmic web stretch billions of light years through space. The universe is so vast, we can't even begin to pretend to understand it all. That doesn't mean we can't try though. And bigger isn't always better. I think living on a tiny planet around an average star is working out pretty well for us so far. I'm happy to announce we have a weekly newsletter to keep up with all the discoveries in our cosmos, and our designer Peter has made the most beautiful email you'll ever receive. Sign up with the link down below. It's the best way to stay connected between videos. Short, focused updates on what's new and fascinating in space each week. No spam, no filler, just the good stuff. You'll get the latest news, visuals, and insights delivered straight into your inbox. If you enjoy Astrum videos, you'll love this. Join the newsletter and stay curious with us.